So the next lecture will be given by Professor Xiaoqing Elaine Lee from UT Austin Physics Department. And she's going to tell us about several different topics that she mentioned to me. And but the original title for her is Magnonics and the different kinds of techniques of detection spin waves, for instance, like BOS. So without further ado, again, let's welcome Elaine.
Is that right? Okay. Alrighty, so I've given everybody a copy of my slide. I did make some updated slide yesterday. So some of the slides you have is a bit outdated. I'd like to talk to you specifically about how to detect magnons. And this is a topic I've been working on for about 15 years. And so my talks is a section according to this outline. After I finish each section, I'll give you a 3 minutes break, have you to ask some questions. I think a 2-hour-long lecture is pretty long, especially this time of the day. And then I don't have to cover all the topics. I'm in the physics department. The topic I tend to choose to work on are driven by physics concept, and also I'm attracted to new materials. If I depends on how the discussion goes, I may go to the last two topics earlier, jump some earlier work, so I can tell you what are the newest things that we're doing. Okay. So without further ado, let's get started. And before I give the lecture, I'd like to get an idea of my audience in the room. So first of all, how many of you study magnons as a research topic? Can you raise your hand? Okay, a few. How many of you study magnon using optical means? Fewer. Right. Okay, so this is good. So I have the introduction material won't be too boring for most of you. Okay, let's get started. So let's begin by discussing what's a magnon. So in a magnetic ordered material, let's say ferromagnetic states, at the ground state level, all the spins are aligned. And you may ask the question, what is the first excited state? Would it be flipping one spin? So the energy cost to flip one spin is decided by the exchange coupling. And it turns out this is not the lowest level excited state. If you share the spin rotation, by having a coordinated spin rotation, you end up having magnon or spin wave. And this turned out to be a lower excited state than flipping an individual spin. So this, because of the spin waves, just like in many ways are similar to phonons. Right? Phonon is coordinated lattice vibration. A magnon is a coordinated spin rotation. So, and obviously to have this coordinated spin rotation, the spin had to be coupled somehow. And depends on the wavelengths, there are different mechanisms where spin can be coupled in a magnetic material. And depends on the wavelengths of the magnon, there are two most important coupling mechanisms. Dipolar coupling, which is responsible for long wavelength magnons, or exchange coupling. As we all know, exchange coupling is very short range, so they're responsible for the short wavelength magnons. And this is on the right here is a picture where the propagation of the spin wave is along the horizontal direction, and then along the vertical direction, all the spin has the same orientation. But you can see the spin rotations are repeating themselves over a certain wavelength. So in many cases, we actually need to consider both the dipolar interaction and the exchange coupling. So this is the mechanism for how spins are coupled to each other and forming this coordinated spin rotation. Okay, So I did say, magnon is an excited state, right? So for any excited state, you need to be concerned about their dynamics. And I'm sure you've seen this many times by now. So the magnon dynamics are simulated by the LLG equation. So in this formalism, basically magnon refer to a small deviation from the static magnetization, and it's a rotation around an effective field. And in this formalism, the precession frequency is the magnon frequency, and alpha is the damping. And then you can actually have, you can compensate for magnon damping through different means. One of the means we heard over and over again in this workshop in the summer school is a spin transfer torque or spin orbital torque. So different torque terms can be used to compensate for damping. So damping are measured in many different ways. One of the common ways to use Gilbert damping alpha in this formalism. And a number, for example, for very typical, magnetic metallic film, nickel iron, alpha is around the order of 0.01. So when we talk about magnon damping, the first thing you want to ask is, am I looking at a metal or am I looking at an insulator? And in different materials, the damping mechanism is different, right? In some cases, in an insulator, for example, is the magnon-magnon interaction and magnon-phonon interaction is a dominant damping mechanism. And there we're looking at a damping on order of 10 to the minus 4. So that's typical for a high quality magnetic insulator. So the magnon frequencies can also vary over a very broad range. Again, if we start with a permalloy, nickel iron alloy, at a modest magnetic field, for example, at 100 or 1,000 Oersted, the frequency is typically on the order of 10 gigahertz. And the line width is on the order of 0.1 gigahertz. And so these are just some typical numbers for magnon in metal. Okay? So then why are we interested in magnons? So first of all, because magnon at a few gigahertz or tens of gigahertz, they're thermally excited at room temperature. If you take the Bose equation, you calculate the occupancy number, and you can find out that at room temperature, the occupancy number for a gigahertz magnon is on the order of 40. So they're thermally excited. And they, as such, they contribute to both equilibrium property and non-equilibrium property. And therefore, it's important to understand their presence and how they influence different spintronic applications. So people use the phrase Magnonics, and it really is about just like spintronics. You add a few letters at the end, you make a field, and there are also valleytronics and various form of technology invented on this term. So when people talk about Magnonics, they really are trying to advocate for magnon-based devices. So this is not the focus of my talk today, but I would say there's some very commonly studied application. One of them is a current tunable oscillators that's based on basically magnetic precessions or magnons. And there are also wave-based computing logic devices. So I'll say a few more words about that. And then how do we excite magnon besides thermal excitation? If we want to build a device out of them, you need to perhaps control the occupancy number or control the damping. You can excite magnon by a resonant RF field, or you can excite them through electric field, through a voltage-controlled magnetic anisotropy. And there's also a lot of people are studying how to excite magnons using ultrafast lasers. And mostly in insulators where they can actually use the laser bandwidth is larger than the energy of the magnon, either gigahertz or terahertz. You can therefore excite them very effectively using ultrafast laser pulses. But probably the laser pulse is not going to be the way to go for application for most applications. But we did during the poster session today, I did see people present on ultrafast wave generation. Basically, it's a magnon phenomenon as well. Okay, so how big is the field? I started working on this field when I was assistant professor, started almost 17 years ago. And I was a little worried at the beginning because it seemed like a niche field. But it's actually a growing field. So this is, I took some of the pictures in this presentation, updated presentation from this article, 2024 Magnetics Roadmaps. And there are pictures that you show later on has a annoying draft across it. That's the only version I can find online. So this is, over the years, the number of publications based on with the title of Magnonics is actually growing over time. So one of the early applications for Magnonics is to construct nano oscillators. And I'm citing some early pioneering work where people have recognized that using spin transfer torque, you can actually pass a DC current through magnetic multilayer etched into a nanopillar geometry, and you can compensate for magnon damping to such a degree that it'll go to what's called the auto oscillation. So you have compensated entirely, it become an oscillator. Very much like laser, because I use laser a lot in my own research. So this is basically having a pumping mechanism, in this case a DC current, to completely overcome the damping and allow the oscillation mode to go into allow this magnon to go into oscillation mode. So these oscillators are very compact, and their frequencies are tunable by DC current. They have a lot of desirable attributes, except for the emission power is low. So it recognized very early on that you need to phase lock multiple oscillators. So this is a result back almost 20 years ago. Where are we now? So I looked at some update. So this is a work published last year, 2023, from one of the leading group in Europe working on these nano oscillators. What they have found that you can actually take a pretty simple geometry and take a waveguide and actually etch them into this, this particular shape. And then these nano oscillator can be synchronized by magnons propagating magnons. And they found that they can, in this geometry, simple geometry, they can actually phase lock about 21 oscillators. They know these oscillators are coherently phase locked because the peak power grow linearly with the n square, n being the number of oscillator. So there's a coherent adding of the amplitude for the emission power. And as that happens, as the power grows, there's also other benefit. So this is the line width, but plotted as 1/n. So a larger number of oscillators are in this direction on the left. So the larger number of phase oscillator you phase lock, you actually get a narrower line width. So this is desirable for a lot of application. So this is the current state of art. You can actually lock about 20 of these nano oscillators and see coherent power growth as n squared, and see the line width actually get narrower. So this is one of the important applications for Magnonics. And another one is logic gate. So I've also seen a few nice posters about building logic gates with spintronic devices. And magnon-based logic gates and computing belong to a general category of wave-based computing. And for all computing scheme, it turns out there's only two type of gates you need to build. One is a 1-bit gate, and this is what this is a NOT gate. Basically, you need to take a bit and be able to flip it, go from 1 to 0 and 0 to 1. So this is done, proposed 15 years ago, and this is basically based on the interference phenomena in a Mach center interferometer. And then realizing these gates are far more challenging. And of course, a lot of time because the finite lifetime of the magnon, limited propagation distance of the magnon. So one really need to find a way to amplify the magnons. Again, spin transfer torque is one of the leading methods to do that electrically. So besides the NOT gate, 1-bit NOT gate, you also need to have a 2-bit gate, or in this particular case, a majority gate are proposed where there are 2 inputs, an A and B, and then there's also control channel. And then an AND gate means that whenever you have the input as both 1, you have output of 1. And then if you have either either bit to be 0, either A or B to be 0, you would have output of 0. So there's a particular scheme worked out to build a control gate, 2-bit gate, or another possible 2-bit gate is called a OR gate. So this actually would have some benefit in terms of compared to CMOS logic. And this again has been worked out quite some time ago. But where are we in terms of the implementation? So a variety of these spin wave devices have been fabricated. And as you can see, the progress is very challenging. You know, there's a few over the years. And to make a fully hybrid computing scheme based on the spin waves, you need to take a hybrid approach between CMOS and Magna majority gate. One of the hard part is we always like to argue that the Magnon are energy saving, but the difficult thing is the conversion process. The CMOS converter to Magnon back to CMOS converter, the energy consumption that's consumed in a converter is actually several orders of magnitude larger than the Magnon energy. So there's a lot of challenge to be overcome to make this Magnon-based computing a reality. So I'm going to skip, be a little brief about the challenges there. One of it is really the efficient coupling between electronics to Magnonics. And also, in order to be able to cascade multiple stages of Magnonic devices, wave-based computing is analog computing. So the output actually depends on the input. So you also have to have what's called the Magnon normalizer. Basically, after you're done with one stage of a logic operation, you need to reset the magnitude so they're normalized. So there's many challenges good challenges for young people to work on. Okay, so there are many things that I won't touch on today, but that are quite interesting to me personally. So because of the challenge associated with the damping in Magnons, people have come up with different ideas. How do I overcome damping in Magnons? One of the ideas is actually work with a hybrid quasi-particle, and perhaps hybridizing a Magnon with a microwave photon, or hybridize a Magnon with a surface acoustic phonon. So both of these hybridized wave or quasi-particle may enjoy benefit of a different type of quasi-particles. Photon, for example, is low loss. And then you can get into this routine of what's called the cavity magnonics, that you can have these two quasi-particles strongly coupled to each other, and therefore there's energy exchange between these two types of quasi-particles. Another frontier in Magnonics is to pushing for the ultimate quantum limit. Oftentimes we're talking about Magnon and spin wave interchangeably. Classically, of course, wave picture is a classical picture. Magnon in itself, I have these embarrassingly naive pictures in my head. The Magnons are like the beans that we eat. They're particle, right, one at a time. So can we handle individual Magnons? Can we manipulate them, or can we entangle them? So we studied a lot of photon entanglement, but there haven't been that many matter wave or quasi-particle in matters that can be entangled. So there's maybe some ideas that you can work on, maybe transfer information through entanglement, right, instead of dealing with the propagating waves. What also have drawn my attention, of course, is our terahertz Magnon, higher frequency oscillations, particularly antiferromagnetic materials, where actually the Magnon damping is reduced because the symmetry will forbid some high order Magnon interactions. And finally, myself and my own group are getting into the topic of topological Magnons. Again, maybe a way to combat damping and loss associated with Magnons. Can we learn from the concept of topology and enjoy some topological protections to overcome the damping problem? So if I get to the bottom of my 80 slides, I'm trying to scare you a little bit here, that I will talk a little bit about topological Magnon, but that is really as a topic that I actually present at a different workshop tomorrow. So let me pause. So I'm done with my first section of the lecture now. basic introduction of what's a magnon, why people are interested in that. I'd like to just give you a 3 minutes question break, or whatever you need to break for. And any questions at this point? Yes, please.
Thanks. Thanks, Prof. About the wave vector range of different region of magnons, just now you mentioned. I wonder what, if we compare about a short wavelength magnon and a relatively long wavelength magnon, which one is preferred in futuristic applications?
Yeah, so I think certainly you deal with both. You know, for example, I'm hesitating because I don't know, it really depends on what application you're talking about, right? So oscillator, for example, I would imagine short wavelength magnon could be very good for high frequency oscillations. So, you know, so there, you know, for example, terahertz oscillator may be based on the short wavelength magnons. But you know, most of the magnon devices that has been demonstrated are fabricated with EV lithography with a dimension on the order of 500 nanometer or so, 100 nanometer to a micron. There you actually have to consider both the dipolar coupling and exchange coupling. So, you know, so there are advantages and disadvantages associated with these short and long wavelength magnons. So a lot of time people tend to think a lot of transport property depends on the size of the device. Maybe the exchange magnon play a dominant role, partially because they seem to have a higher density state. But that is not always the case. You know, so I think that's a great question, but you know, typically you need to consider both.
Yeah, thanks.
Please.
And I want to ask, why always we have to apply a certain amount of external field to define the propagation direction of magnetism?
Right. So, you know, magnon is a small, you know, it's a precession around a saturation magnetization. So actually magnon, I'll cover that later on, depends on I think the magnon without a saturated moment is ill-defined. So typically you need to establish a saturation magnetization, and then depends on the propagation direction of the magnon relative to the saturation magnetization. The dispersion can be very different. Okay, so this is how people work with well-defined magnon mode.
Thanks.
Yeah. Other questions? So I think one thing I want to, okay, you have a question. Go ahead.
Thank you. I want to ask that what is particularly ultra-fast laser? I'm not so familiar with it, so can you give me a quick picture of it?
So ultra-fast laser are laser pulses with a duration of a picosecond or shorter. Okay, so you know, I think people in this room, most of you don't deal with it because you're working with microwave and. But ultra-fast laser typically it depends on the technology you generate the laser, have a wavelength of micron to about 500 nanometers. Okay, so when you are pushing for the speed, a picosecond is actually a full oscillation for a terahertz mode, right? So in order to understand the dynamics, people actually use ultra-fast laser to study damping on that time scale.
Okay, sure, thanks.
Other questions? So I just want to say magnons are there, whether you studied it or not. Okay, so because just like phonons are there, in all solids, it may not be the focus of your own study, but a lot of time it's one way of thinking about the deviation from a saturated moment. So switching happens is because you perturb the saturated moment to such a large degree it flips to another configuration. So it's really interesting how the the subgroup of people in IEEE magnetism society are growing, getting more familiar with the magnetism, with a Magnon concept. I would say 15 years ago, if we go into a conference talk about Magnon, maybe 10% of people have, 5 to 10% of people have thought about it. I think today maybe that number is 30 to 40% people have been thinking about how can I use this well-defined precession mode for something, where even if I don't want to use it, what is these mode, what is it doing in my devices, right? So I think this is a growing concept in magnetism, I would say. Other questions or comments? Okay, if not, I'm going to start the second part. So how do we detect spin waves? I'm going to use the word spin waves and magna interchangeably. As you all know, these are just a wave and particle duality. Depends on what kind of measurement you're doing. Sometimes it's easier to think about a wave picture, but other times it's easier to think about the particle picture. So for most of you, maybe most familiar technique is FMR. So what's FMR mode? You characterize a lot of thin film using FMR. FMR is actually k equals 0 precession mode. So there's the wavelength is indefinite. Spin, every spin has the same phase and same orientation. And the modes are defined, can be varied by the sample geometry. Another technique is called the neutron scattering. A neutron scattering is often used to characterize Magnon dispersion over the entire Brillouin zone. But the downside of neutron scattering, the interaction strength is very weak. You actually need to grow large amounts of single crystal to do a neutron scattering experiment. And then of course, GMR effect is also a lot of you are familiar with. It has to do with, in a multi-layer structure, depends on the orientation between the free layer and the reference layer. The resistance through the whole stack changes. If you induce a spin wave mode in one of the layers, you will actually see your resistance measurement show oscillatory behavior. And that's actually your measuring Magnon mode when that happens. So I won't be talking about really the first three, mostly, for example, the spin oscillator measurement I showed you earlier is basically a GMR measurement of the Magnon. So I'll be mostly talking about optical measurement, and specifically inelastic light scattering technique. So many of you also work on MOC. I've seen quite a few people presenting on MOC measurement today. And this detects the rotation of the polarization of light. And if you do a MOC measurement using ultrafast laser, you will actually see oscillation in your optical signal in the polarization rotation. That's caused by magnons, open time magnons. But today I'm mostly focusing on inelastic light scattering. So I'll show you a few examples of looking at magnon using what's called the Brillouin light scattering technique. It's actually completely equivalent to a more familiar technique called Raman scattering. So for those of you who knows or have even done Raman scattering experiment, raise your hand. Okay, 15% of you have done that. Raman scattering depends on your experimental demand is such a simple measurement. I like to say we can even train theorists to do it. So it's very, very standard measurement. Okay. And then the far more advanced version of that is called the resonant inelastic X-ray scattering. It's a shared, large-scale facilities. Again, can be used to map Magnon dispersions. So I would not talk about that today. So I'll give you examples, mostly early part using Brillouin light scattering to study gigahertz Magnon in magnetic materials. And later on, more recently, we've also been using a very mundane, very commonly available technique called Raman scattering to study Magnons. And of course, many of you have heard about quantum sensor, a nitrogen vacancy-based quantum sensor. And you can actually detect the noise in those quantum sensors. And you also use a optical detection, what's called optically detect the magnetic resonance to study magnetic structures. You can certainly study magnons using quantum sensors as well. But each of these topics could be entirely different 2-hour-long lectures. We only have 1.5 hours left, so I'm going to focus on inelastic light scattering. So my own group is an experimental group. We study, we use light. We literally shine light on the material. We study these quasi-particles. Okay? So we study both magnon, phonon, and plasmon, and also irrelevant for today's talk, excitons, electron-hole pairs. So it's a polarization wave. So all of these has a wave picture and the particle picture. And in fact, many of you have done Raman scattering. If you think about what's a Raman scattering, it's identical to brilliant light scattering. The instrument is very different though. It makes a difference for experimentalists. The idea is you come in with a photon that has a very well-defined frequency and the wave vector. And in the process of interacting with some quasi-particle in the material, it loses this scattering process obeys both the energy conservation and momentum conservation. Part of the photon energy and the momentum is transferred to the matter wave, or it can actually increase the frequency. So in the Raman spectrum, you actually have what's called the stope peak, anti-stope peak. So this is the incident laser. If you absorb a phonon or magnon, you end up with an anti-stope peak where the frequency of the outgoing photon goes higher. But many times the stope peak is stronger, especially when the frequency gets larger. So in that process, the photon actually loses energy because it's creating a magnon or a phonon in the process. Okay, so Raman spectrometer is basically based on a grating, and you just shine light on it. You separate the Rayleigh scattering, which are the photon that has not been scattered, interact with the matter wave, but to a very small percentage efficiency, you have stoke and anti-stoke peak. So most people don't understand this. Actually, Raman measurement is a single particle measurement, meaning vast majority of the time, you don't get either stoke or anti-stoke peak. You're actually waiting for a long time for that scattered photon to arrive. When you measure a single photon, single scattered photon, you actually created one quanta of magnon, where you annihilated one quanta of magnon in the material. So that very mundane process is already a single particle process. It's a quantum process. Okay? And for experimentalists, brilliant light scattering instrument is much harder to use. It involves multiple scanning fiber pearl cavities. So those of you who have some background in optics, anytime you have a cavity, you have these modes, longitudinal modes. Just like playing an instrument, you can only form standing wave of a certain frequency, right? So this is called the fiber pearl mode. And the two cavities have different length. In fact, the scattered photon run through these two cavities multiple times. And you have such great rejection rate, you can pick out one photon out of 10 to the 8 or 10 to the 9 photons. And that allows you to detect this very weak scattering process coming from magnons. Okay, I don't want to spend too much time on the instrument because I think most of you don't do this type of experiment. So in the last 20 years, two groups in Germany in particular have really made this a micro BLS, basically focus your laser beam down to a micron or half micron size, and be able to map out magnon in the microstructures spatially. They have really